Good morning. I am Yinghan from Purdue University. Today I'm going to present our paper about complexity-aware adaptive distributed AI systems. We will first talk about the purpose of designing such a distributed system and define complexity. Then we will describe the proposed system, which is composed of a mainnet at the edge and the cloud. After that, we will explain complexity-aware strategies, and finally, we will show the experimental results. Using only edge or cloud for machine learning has limitations. For example, due to resource constraints, it's hard to train deep neural networks at the edge, and if we use pre-trained models, it cannot adapt to the environment. Uploading all data to the cloud is not efficient considering the communication energy and latency. And therefore, we propose complexity-aware adaptive distributed systems which take advantages of edge-cloud collaboration. And our system considers both class and instance-wise complexity, which is measured by the entropy of instances and force discovery rate of classes. For a distributed system, it is important to use intelligent collaborative strategies. In a nutshell, our approach pre-trains the model on the cloud, then fine-tune it locally. During inference, the cloud helps the edge process complex data. The mainnet has three parts. The main block is a pre-trained part. The extension and adaptive blocks are trained on hard classes to improve the accuracy. And in a system, there could be multiple nodes and users. In that case, the main block may be shared by the users. To convert a regular neural network into mainnets, we may either divide it into two blocks, then add the adaptive block, or we can also use a complete neural network as the main block and add two blocks. The adaptive block is the lightweight version of the main block, and the sub-blocks with the same color have a similar architecture, while those in the adaptive blocks have fewer number of layers. The outputs of the main block and the adaptive blocks are added or concatenated to be the input to the extension. To train our system, there are multiple steps distributed to the edge and cloud. The cloud is responsible for pre-train the main block and determine easy hard classes based on validation accuracy. Then, the main block is downloaded to the edge and we fix its weights. We use only data from hard classes to fine-tune the extension, and the adaptive block creates a short path for backpropagation and provides features for hard classes. During inference, all the instances will go through the main block, and it detects whether an instance belongs to any hard classes or whether an instance is complex based on the entropy of the prediction. And only instances of hard classes will be sent to the adaptive block and the extension block. And we also compare the predictions from the main block and the extension block to select the better one. And only complex instances are sent to the cloud for further processing. We evaluate our distributed system by extensive experiments using modified models of ResNet and MobileNet, which has inverted residue blocks, and we evaluate them on CFAR100 and ImageNet datasets. And here is how we modify the MobileNet v2 into a MEA net. The results show that our proposed model has a stronger ability to distinguish between hard classes. It has achieved 5 to 10% higher accuracy on hard classes. However, the improvement shrinks to 1 to 2% on all classes because the easy hard class detection is not 100% accurate. In conclusion, the advantage of our model is maximized if the instances of the hard classes make up a large proportion of the dataset. We also estimate the cost for training. Our system is able to reduce millions of computations by fixing weights because it does not require gradient computations. And it also alleviates memory requirements. Here we show the results for edge cloud distributed inference. By adjusting the threshold for complexity, we can control the percentage of data sent to the cloud. With distributed inference, sending 50% of data to the cloud can make the overall accuracy the same as the ResNet 100 on the cloud. And finally, we use this table to estimate energy cost for distributed inference. We can see that the distributed system consumes lower energy than cloud computing. And again, we can control the accuracy to energy trade-off by adjusting the threshold for complexity. Thank you for watching, and please feel free to ask any questions.